Okay, let's look into slope fields. And if you are a random passerby on the internet and you want a hard copy of these things that you can write on, and for this one, it's going to be very beneficial to have a hard copy to write on, and you'll see why in a minute. You can go to this bit.ly link, bit.ly/slope field intro, and print one for yourself. So let's talk about what a slope field is. And it is a tool that enables us to sketch the graph of the solution to a differential equation, even if we don't have the actual equation of the solution. So if we have the differential equation, we have some representation of the slope or the derivative of the solution, and we can use that to sketch the solution even if we don't have the equation. So what that means, and we're looking at number 3 on that sheet I referenced a minute ago, is we will use our knowledge of the function based on the differential equation to sketch the solution. And for this one, we're going to sketch a solution that passes through the point 0, 1. So I have x, y coordinates, and I'm looking at the coordinate 0, 1. So I know my function is passing through this point, and for a minute, just watch. Please don't write this down. I will tell you when I'm ready, it will be better for you to go ahead and start copying what I do. But at this point, I know my function is going through here. It's going through that point. And since I know the derivative, since I know the differential equation, I also know the slope of the function. So the slope of the function is found by adding the x and the y coordinates. And if I add 0 and 1, I get a slope of 1. So what I know is that my function, as it passes through this ordered pair 0, 1, I will have a slope of 1. And so I'm just going to draw a tiny little piece with a slope of 1. Now I could extend that. If I know the slope is 1, I'm trying to get that to be closer to 1. If I know my slope is 1, I could extend that slope of 1 until I get to my next nice ordered pair, which in this case, I get to the ordered pair 1, 2. And if I add those coordinates, I now have a slope of 3. And we can now adjust my slope as we get to different ordered pairs to represent, in this case, a steeper slope. I could also carry it on to the left. And what I just showed you there is actually more closely related to something called Euler's method. But that's essentially what we're going to do with slope fields. We're going to use the differential equation to get representations of the slope of the solution, and we use the slope to sketch the graph. So on to the actual slope field, and here's where you can start writing stuff down. We are going to do kind of what I did at the point 1, 0. I'm looking at this point, and at that point, I know my function will have a slope of 1. So I sketch a tiny little sketch of a graph through that point with a slope 1. And we're actually going to repeat that for every point that you see here. And so if I go over to the point 1, 1, if I add those coordinates, my slope is going to be 2. So if I pass through this point, I'm going to sketch a tiny piece of a line with a slope of 2, which is going to be a little bit steeper than that one. So that's about 2. If I go to my next point, that is the ordered pair 2, 1. If I add those coordinates, I get a slope of 3. So through this point at 2, 1, I'm going to sketch a small piece of a graph with a slope of 3. And so it looks something like this. And they don't have to be precise. I'm not like going to get out a ruler and make sure that your slopes are perfect. But as long as they're relatively reasonable, I'm going to be okay with that. A little piece of advice, what I like to do as I sketch these slope fields is this one right here. I knew I was supposed to have a slope of 2. So I kind of imagine a slope of 2. I could go up 2 over 1. I don't have a point up there to look at. I could go down 2 and left 1. And I could look at this point and I just imagine a line that connects these 2 points, except I only draw the small piece of the line right there. So it kind of gives me something to aim for to draw my slope field. Let's go on and finish these on the left side. So I could go -1, 1. And if I plot that point, or if I add those coordinates, I get a slope of 0. So we're going to draw a small horizontal segment. And then if I move over here at -2, 1, we get a slope of -1. And so my slope is going to be -1. And so I'm going to imagine connecting it with a slope of -1 right there. And we will repeat this for every other dot. Now, this is incredibly mind-numbingly tedious. And I'm going to pause the recording and complete this one and talk about some ways that we can kind of expedite the process on these slope fields. Okay, so here's my slope field for this one. And what you'll very frequently find as you are generating slope fields is that they tend to follow trends, that you very frequently will find trends. And if you look at each of these rows, as we worked from left to right, my slope always increased by 1. So this is a slope of 0 at negative 2, 2. On to the right, I was increased by 1. That's a slope of 1, then a slope of 2, then a slope of 3, then a slope of 4. And as you start to identify those trends, it makes it a lot faster. That took me about 20 seconds to do all of that. So I really didn't pause the recording for that long. So look for something like that. And that is the slope field. So we're actually done generating the slope field itself. Now on to sketching the solution. What I know is that my solution passes through this point, 0, 1. And so I'm going to start, if you're supposed to go through the point 0, 1, please just start at that point. And then I look at these little slopes that I've drawn, all these little slope fields, and I kind of think of them as like direction or arrows telling me which way to go. And some textbooks will refer to slope fields as direction fields. And so I know I'm starting with a slope of 1. So I'm going to draw that little piece with a slope of 1 that I did a long time ago. Only now, if I look at my slope field, I can tell that as I move to the right, my slopes get steeper. So I am increasing. I have a positive slope. And as I move to the right, my slope's going to get steeper. So I'm just going to kind of follow that trend. And we're going to be concave up going through this section. That's really bad. Try that again. Concave up going through this section there. And then if I work my way to the left, I notice this little section of 0 slopes right here. As I get through that, so right here, I'm just going to highlight. Actually, I will use the highlighter. I'm going to highlight this section of 0 slopes right here. And as I get to that point where my X and Y coordinates are opposites, I will have a 0 slope. So when I get to that spot, I should be horizontal. So I'm going to come back, and when I get to that little blue region, I should be horizontal. And then right here, I see a group of -1 slopes that line up. Whenever you have slopes in a slope field like this that kind of all line up and they're pointing in the same direction, that actually creates asymptotes. So we have a slant asymptote, and I'm going to come up and just approach that slant asymptote right there. And that is how we are going to sketch a reasonable graph of the solution that passes through a given point. Now, a little bit of vocab that I may mention at some point in class, or you may see at some point in your class if you're a random stranger. If you are ever able to group a bunch of slopes that are the same, we call that an isocline. We call that an isocline, which iso meaning same, cline meaning like inclination, incline, slope type thing. Inclination may have been the wrong word. But any grouping of slopes that are the same. So that is an isocline of slope 0. If I look at this section, this is an isocline, and all of those have a slope of -2. So isoclines do not have to be a 0 slope. They just have to be the same slope. Isocline of slope equals 0 here. This is an isocline of slopes that are equal to -2. So a little bit of vocab there. And isoclines like that slope of -1 right here, that does turn into an asymptote because they all lined up. So there's one slope field. Let's look at a different one. I'm going to go a little bit faster on this next one. Can't believe I spent 8 minutes on this so far. But, where's my mouse? There he is. Okay. So on to this one's number 5. We have the differential equation dy dx is y minus 1. And this one's going to be a little bit easier because my differential equation is only dependent on the y coordinates. And so let's see what happens. I'm going to start here at -2, +2. And so right here, my y coordinate at -2, 2. My y coordinate is 2. My slope would be 2 minus 1, which is 1. So I'm going to have a slope of 1 right there. This point right here is the point -1, 2. My y coordinate is 2, and so the slope is 2 minus 1, which again is 1. And when your differential equation is a function of y, it's really nice because once you get one point, all other points with the same y coordinate will have the same slope. So all of these with a y coordinate of 2 will have a slope of 1. Right here, when y is equal to 1, 1 minus 1 is 0. So every single one of these is going to be 0. Makes it a lot easier. And then I'm going to do this and finish up the rest of these. Okay, here we go. That took me about 10 seconds. But there are all of the slopes for this one. And you'll notice that the rows are always the same because if you move left and right, you're not changing your y coordinate, which is the only thing that affects the slope. So our rows are the same. And let's say I wanted to sketch the solution through the ordered pair 1, 1. if I started at the point 1, 1, and I wanted to sketch the solution through that point, I'm going to start by plotting the point at 1, 1. Always start at the point they suggest. So I'm going to start at the point 1, 1. And I notice that I have a 0 slope. So I'm going to be horizontal as I go through that point. Well, since I'm horizontal, my y coordinate never changes here, which means my slope is never going to change either. So the solution through that point is actually a horizontal line. It just sits on that. Wow, I kind of got off of it a little bit there. But there is the solution. And when you have a horizontal solution like that that sits on a bunch of 0 slopes, we call this an equilibrium solution. An equilibrium, that is horrible writing, but that says equilibrium solution. And we call it equilibrium because the value never changes. It's in perfect equilibrium. It's always equal to the same value. So we call that an equilibrium solution when you have the horizontal solution to a differential equation. And we could even write the equation of that, and it would be the solution in this case would be the equation y equals 1. So there's that one. And let's look at one more. And this one, dy dx, is a function of only x. And so we're going to have a similar trend to this one that we had on the last one. And let's start with this point right here. At that point, my ordered pair is negative 2, 2. And your x coordinate is negative 2. And so negative 2 plus 1 is negative 1. So at this point, when my x coordinate is negative 2, my slope, negative 2 plus 1, is negative 1. And that's going to be true for every point that has a slope that has an x coordinate of negative 2. All of these points, negative 2 plus 1 is going to be negative 1. So I can go ahead and fill in every one of these where the x coordinate is negative 2. When x equals negative 1, negative 1 plus 1 is 0. So I'm going to have a bunch of 0 slopes all the way through here. And it's going to be the same. Your column is going to be the same. Once you get 1, go ahead and fill up all of them in that column because the y's, as you change y's, as you move up and down, will not influence the slopes at those points. And here's what you should have ended up with. And I'm not going to sketch a solution for this one, but I just wanted to do one as a function of x so you could see that the columns will be the same. Now for this one, this is the same thing as saying y prime is equal to x plus 1. And I said I'm not going to sketch a solution. I'm about to do it. If you know that the derivative of a function is x plus 1, you should know that the function itself would be x squared over 2 plus x, and technically plus a c. And so I'm thinking about that, and I know that if I graph a function, x squared divided by 2 plus x, I'm going to get a parabola that opens up. Well, let's look at this slope field. And let's pick a point. Let's just pick our 0, 1 again. If I start sketching the solution right there, if I follow the general trend of these slopes, I have a positive slope. But as I move to the right, my slopes increase. As I move to the left, I see a bunch of 0 slopes right here when x equals negative 1. So when I get to x equals negative 1, I should be horizontal. So I'm going to be horizontal right about here. And then as I keep moving to the left, my function is going to go up. And so if you sketch a solution, you will see that the solution does actually end up resembling a parabola that opens up, which it should, because our differential equation suggests that the solution is an upwards opening parabola. So one last thing, let's kind of look at all of these trends in slope fields, and I've mentioned some of these. And this comes in handy, especially on the AP exam. If you're an AP Cal student, they often will give you, in multiple choice, they'll give you a differential equation, and they'll say which of these slope fields matches the differential equation. And a lot of times, knowing the general trends of certain formats comes into play. So right here, we have 3 differential equations. Actually, I'm going to write it up here. This differential equation, number 5, dy dx, is strictly a function of y. There are no x's that are influencing that differential, that slope. This differential equation for this number 1, that was strictly a function of x. So that one's a function of x. This one, number 3, dy dx is x plus y. That is a function of x and y. And if you notice that your differential equation is strictly a function of y, the rows of slopes will always be the same. Okay. So in a multiple choice situation, if they give you a differential equation that's strictly a function of y, and you notice that the slopes change as you move left and right in one of the options, you could eliminate that one. If your differential equation is a function of x, your columns of slopes will always be the same. And lastly, if your differential equation is a function of x and y, you will notice that as you move left and right and as you move up and down, the slopes change. We don't have those nice patterns, and those tend to be a little bit more difficult to sketch. My pen disappeared. There he is. So in these problems where your differential equation is a function of x and y, slopes change both horizontally and vertically. That's kind of a weird way of saying that, but as you move left and right and as you move up and down. And then the very last thing I'm going to mention, another vocab word for you. If a differential equation is a function of y, we have a name for that, and we call that an autonomous differential equation. Autonomous. We do not have, as far as I know, a fancy name for the other two. But if you have a differential equation that's a function of y, it is autonomous, and you know that rows of slopes will be the same. And I think that is a good enough introduction to slope fields.